One of the things that I do is volunteer at the National Air and Space Museum in the National Mall building at the Phoebe Waterman Haas Observatory. And this is an observatory on Independence Avenue, not too far from, just outside the food court there at the National Air and Space Museum. As a volunteer, I certainly get a chance to interact with a lot of people from all over the world. And by the way, anyone who's interested, I highly recommend it. You don't need any real special qualifications to be a volunteer. And most of the Smithsonian entities do have volunteer programs and openings. Needless to say, we do a lot of astronomy outreach. I'm a volunteer with the Astronomy Education Department. And so as such, over the years, I've got a few tips of things that I found useful in public interaction. For starters, it's helpful to show some passion for the topic. It goes without saying. I also like to include artifacts for hands-on experience if it's possible. What's really important is limit the number of major concepts that you want to get across. And so you don't want to do any more than 2, maybe 3 of major concepts when you're talking to the general populace about science. Solicit input from the audience. And if you can, tell a short story. And that also sort of gets people interested in following the train of thought. Try and make analogies to everyday experience. Keep up with the popular press stories about astronomy, because 9 times out of 10 you're going to get asked about them. And so it really is helpful to know at least a little bit about what they're trying to pull over on the public there, like the latest one on, what is it, Planet 9, and any day now it's going to start shooting comets and asteroids to the Earth, so you have to keep up with this stuff because people are going to ask about it. And finally, use humor judiciously. So, when we do our outreach, we act sort of as astronomy ambassadors. And as part of our astronomy outreach activities, we need to communicate unfamiliar and difficult concepts to our visitors whose knowledge of science varies widely. So, just 1 or 2 thoughts. Well, what have you found that people have difficulty grasping in terms of the type of astronomy that we do? Yeah, I put down a few myself here. So, distances to stars and galaxies. Curvature distortion of space due to mass. We actually have a nice discovery station on that at the Air and Space Museum. The expansion of the universe. Quantum anything. So, we're going to talk about the Big Bang. In the 1920s, Edwin Hubble and others measured the distances to galaxies as well as their redshifts. And he found a bit of a relationship. Farther away something was, the faster it was moving away from us. But the theorists actually had him beat. And so in 1922, Alexander Friedmann developed the idea of an expanding universe consistent with general relativity. And in 1927, Georges Lemaitre, who was a Belgian priest, but got the best education because he got his doctorate at a school, MIT guy, developed independently an expanding universe cosmology, and he also explained the correlation of distance and redshift as evidence of it. And in 1931, he proposed the idea that the universe expanded from a primeval atom, or as he called it, cosmic egg. Now, the eminent British astronomer Fred Hoyle, he didn't like that idea. He preferred a cosmology known as steady state. So he decided to essentially this expanding universe idea, and he called it a derogatory name, the Big Bang. Unfortunately for him, it stuck. And in 1964, Arno Penzias and Robert Wilson accidentally discovered the echo of the Big Bang, the cosmic microwave background radiation. And so they became accidental, actually winners of the Nobel Prize by accident. But there was a problem with it, and so the problem had to do with something called the horizon problem, which in effect says the universe is a lot bigger than we would expect it if it started when we thought it did. And so a couple of people, Alan Guth in 1979, followed by Andre Linde in 1981, devised theories of cosmic inflation to solve this problem. And Guth is also an MIT guy. And in fact, he wrote a book called The Inflationary Universe about it. And I do actually have a book by Hubble too. And Fred Hoyle as well. So they all did a lot of writing. And the cosmic inflation said that in a very brief period of time, the universe expanded pretty dramatically, on the order of 10 to the 26 times or something like that. So, there you have it. But when you see something like this, and this, if you do a Google search on the Big Bang, you'll typically come up with images like this. Something that sort of gets the geek in you going. Not quite right. Again, it shows an expansion into pre-existing space. So, yep, explosion into empty space, but one that always gets me is, where's the observer? You think about it, the observer is somehow outside of all this stuff. So, that's kind of a misconception, I think. And so why is it depicted in that manner? Well, given the name of the Big Bang, we kind of expect a big explosion, right? And animators know how to produce a big explosion and the associated sound effects. So they give us this depiction of the Big Bang. And of course, another common question, of course, is what was there before the Big Bang? Bang. So, thinking about this, and there may be other answers. I'm not saying this is definitive, but my best answer is nothing. I figured a good part of this talk would be about nothing as well. And so you've got a challenge here as an explainer. How can we envision nothingness? And then how can we use that to correct the common misconception about the Big Bang? So, yeah, how do we envision something from nothing? Well, we start by thinking about nothing. Concept of nothing actually have a difficult time envisioning nothing. You know, our world is so full of stimuli and all that kind of stuff. Actually, to have no stimulus is kind of weird. And so think about it in terms of mathematics, what a powerful concept of nothing is in terms of arithmetic, concept of zero. Like, did anyone know the Roman numeral for zero? Isn't one. They use a word. How about the set theory? You have the null or empty set. And even in database lingo, you have the concept of null, or the is null function, or whatever. No instance in terms of database table. So it sort of got me to thinking that there's a sort of paradox about null, and that is that we need something to represent nothing. Oh, before the Big Bang, well, what should we call the nothing prior to the Big Bang? Nope, nothing here. A whole lot of nothing. So, I decided I'd give it a name and call it the null universe, or the nulliverse. I mean, we've got multiverse for multiple universes, so why not nulliverse for null universe? So let's envision the nulliverse. So how do we envision a place with no place, and a there that's nowhere? So let's make some practical compromises. We do make some to envision abstract geometrical entities. For example, when we talk about a line, even though it's a one-dimensional abstract entity, we really use 2 dimensions to represent it. I mean, if it didn't have any width, you wouldn't be able to see it. We wouldn't know it's a line. How about a point? You have 2 dimensions to represent 0. So, and just before we talk about the nulliverse now, when we make these compromises, let's also pay attention to the envisioner, or what we might call the observer. Some people might think of this as the mind's eye, but I'd like to use a different phrase, and I would like to call it point consciousness. I'm using that phrase because I want to emphasize the fact that the observer, or the point consciousness, has no dimension. So it takes up no space. Okay, so I think we're ready to envision the nulliverse. So I would say imagine a dense charcoal gray matrix. You may have noticed that I have cleverly used a kind of off-black color as the background for this presentation. And the reason why I like to do that is because if it were perfectly black, then we would think of it as empty space. And therefore that the point consciousness, the observer, could move around and change location. And that can't be when there's no place to move. So a dense charcoal gray matrix that prevents movement. Nothing changes in the nulliverse. Therefore, there are no events. And so the point consciousness would not experience time or space. There's the start. So now we're ready for the Big Bang. Now, and this is sort of a composite, really, of what you would observe, because there actually are a number of epochs that are rolled into here, and epochs, they have 6 epochs that take totally less than 10 seconds. But you have the Planck epoch, which goes to 10 to the minus 43rd of a second. The brand unification epoch, which is 10 to the minus 43rd to 10 to the minus 36. The inflationary epoch, 10 to the minus 36 to 10 to the minus 32nd second. The electroweak epoch, 10 to the minus 32nd to 10 to the minus 12th. And what really got me when I was looking all this stuff up is that they say approximately. Now, with such small numbers, what's the error bar?
100%?
Yeah, you know, it's like about. Then you have the quark epoch, and the hadron epoch, and the lepton epoch, and finally the photon epoch. But what this means is really that although the Big Bang is talked about as an instant, it really is a bunch of different things happening up until about 380,000 years after the moment of the Big Bang. And most of that time is taken up by the photon epoch, which means the universe was filled with photons. And so when we think of something filled with photons, we think of white light. And so that's my depiction here, and I'm sticking with it. And you can see it's a little bit less than dramatic. So it doesn't give the bang as the animators would have it. But I think it's a more appropriate way of looking at it. So, although I said it's been a talk about nothing, in a way, it's also been a talk about everything. Thank you.